I will cover that later when we move on. Good. So what is the typical process chain we follow in additive manufacturing? So this is generic process chain. So when we want to use additive manufacturing, the first question you should ask, what cannot be done by additive manufacturing? Okay, that is important questions you need to ask. Right, so just because it's fancy and then you want to use it, then that is not the way you should do that. The important question or lesson you need to first learn is which of the components cannot be manufactured by additive manufacturing. So additive manufacturing is not going to replace everything. Okay, it is going to be one of the techniques of producing the components. So the questions should be asked whether that is very unique. The color I showed, it is very unique because it has a multi-material combination, a very unique design. In the conventional manufacturing, we need to completely machine from a block and then weld it. So a lot of interfaces which can deteriorate the service performance. Okay, so first question we ask to analyze whether the materials which we use can be printed. Okay, and if it is printed, then it is possible to produce the defect-free components. So feasibility studies we carry out, and then once we done that, so then the second step is important to analyze the behavior of that material during deposition. Okay, so I see that in a nice example of FEM in additive manufacturing. It is the major step we carry out once we arrive at material and process. So whether it's suppose if we decide to go for tandem MIG, doing this kind of deposition, so how the part is going to evolve, whether a distortion is going to happen, if distortion is there, how we can mitigate it, how the temperature gradient is going to evolve, because I will come back to that. Okay, because temperature gradients under solidifying molten pool, when a well pool from the well solidifies, temperature gradients are going to dictate the microstructure, how it is going to evolve. Okay, so therefore we carry out extensive FEM simulation, which is inherent part of it. And both the feasibility study and the FEM analysis we carry out would understand, would give us knowledge about, so how complex is the process and the design complexities we can involve. So once we have that, then we convince ourselves that this part can be printed. So next is to again the robotic part generation manipulation. Okay, for that we'll have to use very careful selection of tools which can give us parts in which the deposition can be made. So once we have that, then the CAD manipulation, which you all are aware, slicing and path planning, which you must all do that by that. So then the robotic programming generated and then printed. And we also use extensive online monitoring tools to monitor the defects. Okay, so again, I'll come back to that. We also use a lot of the AI-based tools for online monitoring. It's also close feedback. Like suppose some defect is forming, you can detect and then you can also completely remake the layer and then start printing again. Okay, good. So once it is done, then the post-processing machining is important. So we machine the surfaces, then get the components used for the end-use applications. Okay, good. So this is the generic process chain. Quickly we'll go. So what are the setups we need? Okay, some of you have seen in the equipment here. Right, so the KBR Institute, they have a cooker robot, and a power source. So power source is the welding power source, and which gives the required current, for generating a constant, low voltage system, the arc. Right, so that is the welding power source which can be manipulated. So advantage is here if you have a complex inverter, thyristor based microprocessor system, because the waveforms what we generate. Those are important characteristics to change the microstructure, properties, and control the defect. Again, I will show the example. Right, so we invent waveforms to engineer the microstructure. Right, so what we start is a system, a robotic system. You can also assume CNC system. 3-axis CNC and a turntable should also work as well. Okay, so and the controller, the welding system starts. So once you have that, you can start depositing the parts. Okay, so this is one of the most and simplistic system if you compare in any of the additive manufacturing. Right, of course, plastic printers are there, material extrusion based. For metals, this is one of the most low cost and simple additive manufacturing tools. What we have for printing in use objects. Good. So again, quickly to brush up, what do we do? The process chain. Okay, once we identify the complexities and then the robotic program has to be generated. So we start with a CAD drawing, you know that, right? Converting that into an STL file. Okay, now we also moving towards AMF file because of inherent problems with the flat faceted STL geometry. So now we are also introducing AMF, additive manufacturing format. Okay, so where we can also negate the curvature of the contours. Okay, so once we have an STL file generated, we do slice and parts are generated. And once the parts are generated, the building programs are added to the part, and then the final parts are deposited. Okay, so all these steps are also supported by the extensive mathematical modeling, and now we also use AI based tool. One example I show later. Okay, good. Right, so one of the biggest advantages of welding based system, okay, compared to powder bed processes. So where here we can also use an adaptive slicing and multi-directional slicing, which enable us to print supportless. So imagine if you want to print an object with large overhangs, heavy objects. So if you use a powder bed based system, we may have to slice in only one direction, unidirectional slicing, and we have to give supports and a lot of machining wastage and then printing time increases. Whereas in here, so we can also use the multi-directional slicing. So suppose if you want to print something like this in a powder bed, then we have to give supports over here. Whereas in by building based processes, if we have a 2-axis turntable, we can also use a multi-directional slicing, and then we can print by manipulating the position. What you see here. So it's the exact system, but we have an IIT Madras, an 8-axis fully integrated system, right? So and we can also do an adaptive slicing where each layer thickness can also be changed. Okay, suppose if you have geometries with non-linear features, curved features, so you can also change the layer thicknesses, and by manipulating welding, the heat input or arc energy, we can also change the layer thicknesses so that we minimize what is known as the staircase effect, so that machining, post-deposition machining can be minimized. Right. So these are the advantages which makes welding-based processes to print large component with overhanging features. The exact component what we printed, maybe we will see that later. Good. So we also use very novel part planning strategies. Okay. So based on FEM simulations, and we arrive at which parts planning, which way the robot should complete the layer by extensive analysis. Say for example, here what is shown as a MAT, medial axis transformation parts. So where suppose if you want to print such layers, so we also manipulate and then identify. First is medial axis, and you start from the medial axis, the central axis, and start printing from the middle axis. Continuously we go, so that the part can be generated without intersections and with minimal defects. Suppose if you start from the contour outside in, so we have the cavities or like fusion and descent. Okay, so these are some of the parts we create. Okay, so both the adaptive slicing and the creative path planning is what we generate based on the FEM simulations to minimize the distortion, for example. So requires a fully integrated system. So what do you mean integrated system? So our robot, and the building power source, and the users should all be controlled in a closed feedback control loop. So for that, we need to have a complete digital twin of the system. Okay, so one such system, we have established in IIT Madras, built by us. Okay, so what you see here is the exact system, what is there in the lab, and we also have made in computer. Right? So what you see here, a simple part geometry. So we have an 8-axis system, and 6-axis robot, and 2-axis positioner. Okay, so what is the advantage of making the digital twin is we simulate the actual parts in the computer first and then generate, and then subsequently these scan vectors. Suppose if you want to print one layer, so each vector when we print, we also load the welding parameters. So what current we need to use to deposit that bead. Right, and subsequently, so when we build layer by layer, so we can program the each vector's welding arc energy okay, continuously, so that we can also introduce required the temperature gradients which can dictate the microstructure, or we can also mitigate residual stress as and when needed. Okay, so once we have such systems, so we can visualize the complex loop part what we generate, and then subsequently we see that how the entire part is built, okay, before even printing in the digital twin, and then subsequently we can take it up for the final printing. So this is one operation, what you see here. So this is one of the aircraft brackets we try to print, right? So we start with the material feasibility, FEM, and all this is that. So now we know that how we are going to build. If you are building 10 mm, how much distortion this part may incur. So we do the corrections in the part planning stage itself, right? So once the part planning is carried out, so we see that how the robot is going to print the part, right? So and this software, what I'm showing here. So this is made by one of our, in fact, one of my PhD students in collaboration with my friends in Europe, where we have a complete replica, twin of what we have in the lab. Right? So subsequently, we generate the required parts required based on the optimization. And the parts are given, and then each part it's also now loaded onto the robot controller, and then robot controller will also control the welding process to get the required currents and then gas flow rates, so that can be printed as we go. And by doing so, we also minimize the errors in terms of integration, and also suppose if robotic access is limited or some interference encounter, we will also correct it there itself, and we can also see how the generated path is going to work in the twins. So once you optimize, next step is to take it and then start printing. So we just press the button, both power source and robots continuously talk, and then part is printed. Right? So why do we need such a complex systems?